But yeah, let's go with Cypher query language. So as I've mentioned earlier, unlike relational databases, graph databases do not really have a uniform query language, but instead, each platform, each system has their own query language. And Cypher was originally built for Neo4j, but it's later opened up via this Open Cypher project. So the idea is that, it's open, that other platforms can use it. But, as I mentioned earlier, it's not yet, there's nothing that is really standard across all languages yet. So preliminary, so we already have like this localhost 7474, and then we want to use the combination of Python Neo and IPy cytoscape. And to do that, we actually you may need to actually like install requirements.txt. So just cd dot dot, and then just do Python, not Python, pip install -r requirements.txt. So that will just install everything, and it says that requirements is already installed. So that's done. So here I'm just using so IPy cytoscape and Python Neo to run things. But you can also alternatively, you don't have to install actually all of this. You can also just use the browser to do all of the stuff that we are using. So it's up to you what you want to use. If you want to use this notebook, or if you want to use this Neo4j console. Okay, so I just load this things up. So you just have to run all of this so that we can prepare, or we can use everything for Cypher, so you don't have to worry about most of this. Let's just finish it. Let's just wait for it to finish running. Okay. All right. So let's start with querying nodes. Actually, let's go first to the slides. So slideshow. So Cypher looks like this. So if we have here's actually how it looks like and how kind of intuitive it is. So here we're trying to find everything that is connected with the gene with the label MAPK1. And we want the relationship to be KEGG. So we want to get all of those nodes, immediate nodes or immediate neighbors of MAPK1 with the relationship KEGG. And the way we do it is first we have this parenthesis. So everything in the parenthesis, we match it with the node. So we say that this gene, the label should be MAPK1, and then everything in the square braces is a relationship. We try to say that we want to match KEGG, and then return everything P, which is P, we equate P with this path. And then for the relationship, so as I mentioned, relationships are directed in Cypher, or rather in Neo4j, but for Cypher queries, it can, it can be agnostic. So you can have the directionality here, but you can also have it like more agnostic, wherein we don't really care if one is a source node and one is a target node. So here, so you can see here, this just refers to any relationship between two nodes in the knowledge graph. And if we're not really querying anything, or if we don't have any filter with if we're not really filtering for relationship, we can also actually remove this. We just have like parenthesis A dash dash parenthesis B. And then this one, we're trying to return connection, wherein the label is KEGG. And then this one, just assign whatever is in whatever matches here to like the variable C. So let's see here in the demo again how it works. So this one, so what we're trying to do here, so we're trying to match. So match is like the keyword that says that, okay, we're going to match everything afterwards. we're going to match the pattern in here. So what it does is that we're trying to match a node with the type is keg pathway, and then the label is apoptosis. And then we're going to send this, or we're gonna whatever matches here will be sent to variable A, and then we're going to return that A. So if you run this, you have something that looks like, why is it not? Oh, there you go. So we have something that looks like this. We only have one node that has the label apoptosis. So that's how it looks like. And so without any filter, I've mentioned this. So our graph database will match any type of nodes and return them. So here, if we do this, limit 5, you just say it will match any node, put it as A, assign this to like the variable A, and then if we return it, we have something that looks like this. So you can have, if you put this as 12, you have something, it just will return to you 12 arbitrary nodes. But if you put something like keg pathway, yeah, it should return to you something looks like this, which are keg nodes. Okay. So next, so for relations, we can have something like this. So if we dissect this query, we say that so these are empty nodes, which means any nodes, but we want this any nodes that are connected with each other via this Go BP relationship. And then, since we have lots of Go BP labels, we just want to limit it so that, it won't explode. And as I mentioned, there's no direction, it can be agnostic. So if we actually remove it and run it, you have something that looks like this. And it's actually pretty much the same if you run it. Oh, it's actually a little bit different if you run it like this, because we want there's some sort of directionality in here wherein the label is like pointed with like a node. So yeah. So you can do either. And then yeah, to query paths. So I've shown this already earlier. So we can query paths by adding like this variable p. So you're just assigning everything here, and then limit 10. So if you run this, then you also have something that looks like this. So we're just trying to find like a path of length 2. So we can actually also extend that. So maybe you want more. So, if you want like a path of length 2, then if you do something like that, then you have, why is it not loading? So this is where like the directionality actually works against our favor, because I mean, there's no more source, and yeah, this is how to properly query it. So yeah, it just, if you have like the direction, you can query like with directions or with no direction. So it does matter. So we start with like so the way we format it is a term, and then this is a gene, and then yeah, so a gene is not a source node to like any of like the other terms. So if we do something like this, then it will return nothing. But if we do something like this, that means this gene is also like a target of that node, then it should return something like this. Okay, yeah. So yeah, so let's try this checkpoint exercise. So let's try to return a query that returns 10 terms that are connected with the gene KL. So let's try doing that. Let me just copy this so that it's easy. So what we can do is that so what we can do here is we can do gene, and then the label is KL. Oh, not that. And then return P. So this should return this, which are all the 10 terms that are connected um, with the term KL. All right. So now this is something I guess for you to try on your own. We can try to create a query that connects the term the gene KL, but we want to limit it with like the relationship KEG. So this one it just returns go BP. So what we want is, yeah, we just got like a bunch of go BP terms because those are like the first thing that it prioritized. But here we want all with the relationship KEG. So you can try that, see if you can have that running. Now, suppose you want to discover, or I guess I should have put it here, like that example is that suppose if you want to discover a path of length 2 that connects gene map K1 to the gene CRKL. So again, there are several ways of doing this, and you can see that there may be some sort of changes or differences with like the results based on how Neo4j um, prioritizes the relationships and the nodes. So if we don't put the limit here, then it will just return um, everything. So that, which is fine, but you know, by putting limits, so there are some sort of like differences in the prioritization. So you can see if I do it something like this, so I just define this is more of like more or less hard coding it, or hard coding the relationship, wherein we just define that this is gene map K1 and then this gene map K2, and then we just want two edges between them, and it will return you something that looks like this. Alternatively, you can use this variable pattern matching. So what this does is that we just tell you that, oh, I just want all the paths with at least, or at most, or no, all paths that is of length 2 between map K1 and CRKL. If I type that, this is a little bit different because, you know, as again, there's like there's this prioritization that is being done with there's a difference in the prioritization between these um, um, two queries. But if you actually remove the limit, then it will look, they were actually just the same, just different priorities. The colors are a little bit different, but it's actually just the same thing. The colors are just flipped between the go terms and the keg terms. But yeah, those are just the same. Yeah, so it's just flipped. Okay. So any questions? Okay. Yeah. So there's also a way to do variable pattern matching. This is really useful. Maybe if you want you know, maybe you're asking, so I want connections between map K1 and CRKL that is at least two edges long, or at most 4. So you can define something like that and have something that looks like this. So yeah, so this one, if you have 2.4, that means you're setting a range of like the path length, and you will return something that looks like this. So again, I guess another checkpoint exercise is that we want to try to finding at least 10 shared genes between go biological process, apoptotic process, GO this ID, and then the KEG pathway apoptosis. So yeah, so I guess I'll leave this as an exercise for you. So this should be easy. You just have to like use this stuff. No, can easily like plug and play this stuff in here. And then another option that you can use actually is this all shortest path. So from the term itself, it just finds all the shortest path between two nodes. So for here, we're trying to find the shortest path between the gene KL and then the gene label PL, or the gene with the label PLVAP, and then return 10. And we see that we actually just have this one, go BP, go BP. So this is like the shortest path between them. But let's try it. Let's see if there is uh, there's like a longer example. Let's see. Let's try this checkpoint exercise, but using all shortest path. So go biological process, and then the label is apoptotic. And then KEGG pathway. And then apoptosis. So return 10.
Just to clarify, so your query syntax, is that SQL?
This is not SQL. This is actually Cypher, which is a different query language that is built for Neo4j. Yeah, so SQL is the one that you're using for relational databases. Yeah. So, and you see here, so this is actually also an answer for this checkpoint exercise, but this one just uses all the shortest path between, looks for all the shortest path between the go term apoptotic process and KEGG pathway apoptosis, and then we just set the limit to 10. So you see here, these are like 10 genes that are connected between two of them.
Those are shared genes that are members of those pathway, this particular pathway in KEGG, in the KEGG database, and they're also in the Go gene ontology tree. They are a part of this Go term.
Yeah. And yeah, if you remove the limit, actually, we can see all of those, the overlaps between them. I'm not sure how big it is. Oh, it's really big, but yeah.
I have a question really quick.
Mm-hmm.
So what is it meant by shortest pathway? Like what is it based on, like the p-value of the gene, or like
so shortest path. So shortest path is not really based on p-value. So what you're doing here is you're trying to find it's traversing the graph. You're traveling across the graph from let's limit this to 10 so that it's easy to see. You're traveling the graph, so you're looking from go apoptotic process, and then of course this is just a subgraph, but imagine this is like a bigger graph and that we ingested earlier. So we're trying to find the shortest path. We're in the shortest path, meaning like the least amount of steps between these two nodes. So apoptotic process, so this is 1, 2, and then just 1, 2. So I mean the shortest path between them is just 2 steps. So all of those so we're trying to find all of those 2 steps path between apoptotic process and apoptosis. So that's what I meant by shortest path. So yeah, so and that means, and to translate that in here is that what I'm trying to find here is basically the overlaps between these two terms, the apoptosis pathway from KEGG and then this go biological process, which is apoptotic process.
So like, does the list of genes that are in both, do they get like ranked and that's how they're the top 10, or like?
No, they're not ranked. Yeah. So they are just there as a set. So with no numbers, but because we converted the set into a network of edges and nodes, so we have a node that is a gene, and that node gene has a connection with no weights to the term. And then we use the network representation to find the overlap between the two sets.
Yeah.
But you could encode each node and edge numerically, right?
Yes, you could assign a weight to each node and each edge, but in here there are no weights.
If you have that data, then
if
you can
do
definitely
enrichment analysis, which we will go into in the next few lectures, you can you will remove, let's say, if you have an input gene set that is from your experiments, and then you will be able to prioritize the overlap of a term based on the overlap between the genes that are in your set. And then you will only visualize a subnetwork that includes those enriched genes and terms.
Okay, thank you.
So yeah, I guess so for more information on Cypher, you can visit Neo4j's website for Cypher manual. And yeah, there are like lots of other stuff that this is just an introductory lesson for Cypher. There are lots of stuff that I missed that you can actually read here.